The next speaker is our very own Mistral Contrastin here at Camford at the Computer Laboratory. His talk will be verifying spatial properties of Stencil computations.
Hello everyone. Who in the room had scratched their head due to off-by-one error? Okay, well, it is very rare that, this many people agree on something so unanimously. And it is good. I will basically show you the nastiest possible off-by-one errors that you can make and how you can basically get rid of them with just about no effort. So I'm going to go over some, why we should do verification, although that has been very nicely modified by horror stories that came before me. And then I will go through a few examples that I actually use numerical code from real-life code and show you how our specification language basically allows you to eliminate bugs. So, why use verification over testing? Well, it has been explained before that testing numerical code is very difficult. Inherently, you have floating point numbers and too many intermediate stages and you rarely get looks at good reference data to check against. Even you can only check against something you know. And like any good computer scientist, when I see something is a hard sell, I quote Dijkstra, and he knows everything very well. So you want to be able to have really high confidence, and testing simply by what it is will never give you that. The other thing is that verification scales very good, and that often raises eyebrows if you say it to a bunch of theoretical computer scientists. But what I mean is that if you pick a property rather than saying my program is correct 100% of the time under all inputs, then you can actually check quite nicely. And I will give you an example of that, that computers might do a better job of giving you coverage and verifying properties. So, this is the boogeyman slide of what went horribly wrong. So a few years back in the States, people working on protein structures had an indexing error in their data. So it validated 3 years worth of work, and they published five papers out of it, including one that got published in Nature. So retracting 3 years worth of work is, basically the worst that can happen. So the tool I showed you, basic principles, would address such issues. And the other one is a lot more famous. It is usually taught to undergraduates, the Mars climate orbiter failure, which is that one component of a climate orbiter sent by NASA was expecting imperial units, but the other component was giving metric units, and it didn't like it very much, so instead it changed its trajectory and ended up in 400 million loss. So if you are not convinced by retractions, then maybe $400 million or pounds might have some impact. The nice thing about this is what I mean by verification might scale better, because both teams probably did a very good job in their individual components, but it is very difficult for a human to have a holistic view of the entire system when the components interact. And so if you have such a large system, then maybe you should leave the bookkeeping to something that knows how to do it very well, such as computers. So hopefully that gives you some motivation. Camford overall is a refactoring and analysis tool. It has various features like use of measure checking and refactoring, but today I will focus on the Stencil specification inference. So very simply, what is a stencil? Some of you probably know it really well, much better than I do, but it is simply, for our purposes, an array assignment that appears in a loop, and the values that you assign change dynamically. So what I mean by that, something like this. So this is discretization of the heat equation. You might be familiar with it. Variables are very descriptively named, as you often find in scientific code. So the loop variable is, we call it induction variable, and on the left-hand side you are indexing based on that, and on the right-hand side you are accessing the vicinity of the operation. So we don't bother with any constants. That is what we mean by dynamic, as in the I is changing at each iteration. If there was a constant variable appearing, then we don't concern ourselves with that. And the eventual aim is that on the right-hand side, you have a nice shape. You have this symmetrical pattern, and can we capture that in a specification? Now, when you show people this, then they think that I will never get this wrong. I'm not going to listen to you because you just solved this toy problem. But in reality, you have code like this. So this is a single stencil computation. The first 3 assignments all flow into the F at the final line. And this is taken straight out of real code, Navier-Stokes fluid simulation. And now you have some indexing variable that you might think that it might be a good idea to verify. So this is the kind of off-by-run error that you might end up doing. And well, as you can see, this is despite the fact that this is a completely different repository, the variables are very similarly named. It is quite consistent, at least in the character usage. But then again, you don't have more than 26 characters available to you. Right, so the execution of this is the heat equation again. The execution basically goes like this, the left-hand side you have U and the right-hand side you have V. And what happens is that as you progress in time, that they progress together. There is no change. So you are time invariant in terms of your accesses. So what can Canford do for you? So you give this code in a file to the tool, which is Canford, and then you say stencils infer, which is the name of the command, and then give the file name, and it spits back this, and possibly this if you have multiple of them. Well, what it says is the central part is, pun unintended, is centered, and what that says is that you are accessing this second point in a centered way, as in that you are symmetrical on both sides. The parameters described, so the depth is that you are going to only access your immediate neighbors, so you are only going offset by 1, and dimension is which, so you can have multiple dimensional arrays in Fortran, so this is used to specify that. Obviously here it is trivial given that it is just a one-dimensional array. The other thing that you might like to note is this read once attribute, which says that none of these accesses for the array V repeats themselves, so you never get I plus 1 twice, and that does actually happen for valid reasons, so it is not always a bug. The nice thing about this scheme is, this is all there is, so you put that in your code and we can check it as consistency. And you did basically nothing. Often, if you're a numerical scientist and you know the differential equation you are trying to discretize, so you already have a nice idea about what the shape is going to look like, your spatial access pattern. So if that is the case, then you just look at it and say, yeah, this looks about right. And you can put it in your code, or if you are trying to bootstrap this in a large code base, you can just say stencil synthesis, and we just edit as a command for you. Now, the nice scheme, this is more of an engineering point about Canford, is that we really believe in commands. They don't get much love in scientific community. So we insert them for you. We intend this to be somewhat descriptive. Obviously, it is much nicer to form a sentence, but in the absence of that, this would do. And the other nice thing is, if you ever decide to not use Canford anymore, then that's just a command. So you don't have to get rid of any pre-processing statements in your code or anything like that. So the kind of mistakes it catches is that, in this case, you have repeated I plus 1 twice on your access to V, and you have said that this is meant to be read once, and this is clearly illegal. So when you run the system, this time not saying inference, but consistency check, then you will get an error, and the exact point that error was generated. The second one is that if you go out of your depth, with I plus 2, while you were saying depth 1, similar thing happened. This is effectively array out of bounds access, except for offsets rather than constant indices. So you've already seen centered and how it behaves. This is extremely similar. Well, it is exactly the same as the heat equation access pattern. We have three other region constants, as we call them, describing things, and this is basically all you need, and some combinators to check just about all access patterns, and we have some empirical data to support that. So pointed is basically that you are mirroring the induction variable. Forward is the right half of the centered, and the backward is the left half of the centered, and it nicely progresses as you would expect. So now another concrete example is you just, you often, if you are doing image processing, you might like to blur things out. And this is a nice matrix capture of the thing, which means that you are taking the weighted sum of all the pixels around you with equal weights, and then applying that as a filter. So you can't write this as a code unless you are using domain-specific language, so instead you translate it into Fortran and you get this. So I tried to write it as nicely as possible so that the indices nicely reflect the grid, but yeah, there is nothing too fancy about it. So how would we go on to represent this, given that we have multiple things going on in each dimension? Well, one thing you might notice is that you have this I-1, I+1 pattern repeating in every column, and similarly J-1, JJ+1 repeating in every row. So, well, you are a scientist, you see that and immediately you think Cartesian product, and that is effectively what we provide with the star. So you write the regions separately, and they are both centered, just like in the first example, and then you say take the restrict them both simultaneously, which gives you something similar to Cartesian product. So depending on your background, you might like to see this as conjunction or restriction, whatever makes it easier to understand, really. And that's it, you just described the whole pattern. Another example is the 5-point stencil, which is used in numerical differentiation. And again, I tried to do some ASCII art and represent it nicely so that it shows you the access pattern properly. And this is pretty much like the previous one, except that you don't have the corners. So you can't use Cartesian product anymore because you are missing some information. You can give some bounds, perhaps, but not exactly. So for that, we have a different pattern, and this time we are focusing on constructing individual blocks, so that red block and the green block, you try to construct them individually with the Cartesian product, and they're quite nicely symmetrical because, well, the equation itself is symmetrical. And what you do is that I want to use plus to choose from one or the other. And that on its own just covers just about every pattern that you can create when you have such accesses, such array accesses. So we said this was a holy grail, so you might be thinking that it is going to look horribly complicated for this one, but mathematics is nice. They often have nice symmetrical shapes, so what you actually get is something like this. You get two stencil specifications because you are accessing two variables, u and v, appearing here. And the first one happens to be that Cartesian product example we did, but it is rather difficult to see when you inspect it like this. And the second one is something very similar. But the whole point is that this is not very difficult, and to start with, you already have an idea as to what the shape is supposed to look like, and you spend no effort inserting it there. You can write it by hand, and then consistency check it, but if you want to be lazy, you can just run the tool, it gives you the specification, it puts it in place, and all you have to do is to check whether it makes sense. If it doesn't make sense, then you potentially have a bug, go debug your code. But if it makes sense, then it is just some extra command you can forget about, and if someone comes and changes this code, refactors it, makes one of these plus ones minus one, then you might catch a bug for free with no effort, and then you no longer scratch your head for off by one error. So how effective is it actually? This is another real stencil, the Jacobi method used in solving systems of linear equations, and the specification above it. So the terms have same coefficients, so you can commute them, well, modulo floating point arrays. And basically, if you just constrain yourself to confusing a plus with a minus, or not using zero offset, but using plus somewhere, there are 6,500 ways of getting this wrong. That's quite a lot. And there are exactly 24 ways of getting it right due to commutativity. And we are going to reject this specification when you consistently reject all wrong ones and accept all the correct ones, which is the sort of thing you expect from your verification. And our analysis is very much at the syntactic level, which makes it, which makes computer scientists very unhappy when you go to conferences, but it is very good for you because it runs super fast. It is nearly instantaneous to analyze any code, regardless of how complex it is, because array operations only have so many things that are flowing into it. So it can do a few more things. I'm not going to cover them in detail, but there are some shapes that are just irregular. So you have emptiness, so your regions don't allow you to express. So you can at least give bounds. So like the 5-point stencil, although it wasn't this shape, the Cartesian product shape, you can use that and say it is at most, so at least it prevents you to do some errors. Not all of them, but some. And you can also use this for convenience if you don't want to write a huge specification. You can name the commonly used patterns, which also happens because access patterns are again used and combined later on, which makes it a bit more descriptive and reusable. And finally, you know, we came up with this: does it actually exist? Well, we looked over a million lines of Fortran code, and we actually looked at UKCA as well, which is full of Stencil code, and about 100,000 array assignments were there of various shapes and forms. We managed to infer 60,000 of these, and we had some engineering problems, so we don't handle all cases, like highly optimized array tiling gives us some problems detecting induction variables. But apart from that, that is still a decent number, and about 5,000 of these are sufficiently interesting, meaning that, you know, if I had two arrays V and U, then I can just do in a loop V indexed I equals U indexed I, and to our definition that's a stencil, but again, we are not going to get this wrong. So these 5,000 of those are sufficiently more complicated. They use more than one regions to express. And our hypothesis was that these 4 basic constants and the operators were enough, and they actually were, because out of 60,000 specifications, only 200 of them had to have at most or at least attributes with them, so they were only approximations to what the shape entails. And that is about it from me. We have great documentation for it, and honestly, it is not going to take you more than an afternoon and a cup of coffee to master the language and then completely forget about all the engineering work that went into it. Thank you very much.
Any questions? Go ahead, Kyle.
This kind of invites the question of what is your next pattern in Fortran programs that you're going to attack and try to identify. I think this could be extended to many, many other things.
That is true. So one of the things was that we initially focused on Stencil specifications specifically, which has this thing that the induction variable appears on both sides. So you make it appear both on the left-hand side and the right-hand side. Except that the specifications can just independently apply to any sort of array accessing, array indexing expressions. So we might generalize it to that, which makes it more applicable. Do you mean like in this space of work, or do you mean in general what more we?
In general, but the basic idea is you're taking a Fortran program which is a rather low level, and you're trying to reconstruct the abstraction from which you're generating.
Yes.
So I think this idea could probably be generalized to many other applications.
Oh no, that is true, and we had
you
some.
Decompile Fortran into a higher level language.
Oh, that wouldn't that be interesting? Yeah, so some people had that, right? So that is sort of a pipe dream, I think. I mean, it is very idealistic to say that I really want to, you know, generate it in its completion from the LaTeX file, from the paper that it was published. I'm going to get the entire code out of it. So there were Newt tried to do that with literate programming, right? You were meant to write your code in the same file that you are meant to present. But that is very difficult to do, so we are just taking these common things, and you said yourself, off by one is as common as it gets, and try to maybe do something like this. And in addition, if it is decent documentation, if it captures some high-level mathematical property, then that's great. But the important thing is that it costs you nothing, and it can be very easily verified, and you just put this in your continuous integration system and forget about it, unless you make a mistake, then it will remind itself.
Any other questions?
Yeah.
What would the workflow be like if so, say you're putting some further specification and the developer says, yeah, this is right, and then at a later date they decide, actually, no, I want to change the loop nesting because maybe this particular array access pattern isn't fast enough, but if I do a reordering, now it's a lot faster, but then they're sort of stuck with the old specification. So
Well, I think that is very similar to the looks sort of situation, which is that, you know, you have some results and the test may say that, or in this case the verification tool may say that it is not okay, and then you have to challenge that assumption. So then you change the specification, but you know that you are changing it for a good reason, as in that you are actually modifying the shape for optimization purposes. I mean, it is just text, right? It's just a command. If you change it, then you change it. The workflow we initially imagined is that the domain scientist already has some idea of the shape. So in the image processing example, you know that you want to draw from your neighborhood indices, so you already know the shape. So you write the shape first and then the code later. The inference was mainly put there because it is too much to ask a scientist to say, oh, you have 900,000 lines of code. Can you please annotate all your array assignments with these specifications? So inference was more of a convenience and integration tool, but it can be used either way. If you are not very sure about what the shape is, then you can actually see whether it makes sense to you.
Can I have a small comment on that?
Sure.
So in some cases, some transformations, the specification will be the same, and so we'll just say this is fine. So if you just change the order of the nesting of the loops, then the specification, the code should still conform to the specification. But if you do things like start changing the order of the dimensions, then you can do a transformation on the specification, but the shape is still the same.
Any other questions? Okay, one round of applause.